Here we consider an electron immersed in an electromagnetic field, and we are going to take a look at the motion of the electron with respect to two different reference frames. One we call K and the other one K prime. And K is quote unquote at rest, whereas K prime is moving with constant velocity v in the positive x direction. And the motion of the electron is analyzed in a small interval of time. So the motion of the electron actually can be more general than this. It can move in all directions, in every possible direction. But in the small time interval that we are analyzing, there will only be a motion along x, and the velocity during that time interval will be constant. So that's the key point. So near the origin of our coordinates, the motion will be along x. But after this small interval of time, we might find that the electron is moving in different directions, as we will see when we write down the equations of the force, because we will see that there is some kind of acceleration along the y-axis and also along the z-axis. So that's important to be highlighted here. Let an electron be at rest at the origin of K prime, which is the moving reference frame. In K prime, the electromagnetic force on the electron will be purely electric, because the electron is not moving with respect to this moving frame. It is moving with respect to K, but not K prime. So in K prime, Newton's second law can be written in this form. We have the mass of the electron times the acceleration, d squared x prime with respect to dt prime squared, equal to the charge of the electron times e prime x. So this is the x component of the electric field in the frame K prime. And then we have something similar for the second component of acceleration, m d squared y prime dt prime squared equal to q e prime y. And of course we also have m d squared z prime divided by dt prime squared equal to q e prime z. In K, the electron is moving at speed v, so these equations will change. They will be different. The Lorentz transformation and the electromagnetic field transformations are used to transform the above equations to the reference frame K. So that's what we want to do. The Lorentz transformations are the following. We have T prime equal to gamma, which is the Lorentz factor, and I'm going to write it in a moment. Then we have T minus V over C squared X. Then we have X prime equal to gamma times X minus Vt. Then we have Y prime equal to Y, Z prime equal to Z here. And then we have gamma equal to 1 over the square root of 1 minus V over C squared. And we also need the electromagnetic field transformations that I discussed in a previous video. I'm not going to do it here, but we know that E prime X is equal to EX, so the X component of the electric field is the same in both reference frames, K prime and K. Then we have E prime Y equal to gamma times EY minus V over C BZ. Then we have E prime Z equal to gamma EZ plus V over C BY. And then we have B prime X equal to Bx, B prime Y equal to gamma By plus V over C Ez. And then we have B prime Z equal to gamma times Bz minus V over C Ey. And now let's set dx over dt equal to x dot, and working with the x component first of Newton's second law, we have d squared x prime dt prime squared, which is equal to d over dt prime of dx prime over dt prime, like this. And we need to find dx prime over dt prime, which is equal to dx prime over dt over dt prime, according to the chain rule. We can also rewrite it as dx prime over dt divided by dt prime over dt. So this will be d of gamma x minus vt over dt and divided by d of gamma t minus v over c squared x divided by dt. So slash dt here, like this. And I have simply replaced x prime with the Lorentz transformation here, and I have used these two formulas here, this one and this one, these two equations. So let's take the derivative here. Remember that we consider the velocity of the electron in this case constant. So the derivative of gamma is 0. Gamma is a constant in this case. We are considering v constant. So we have gamma times x dot minus v over gamma 1 minus v over c squared x dot, like this. This can be written as x dot minus v over 1 minus v over c squared x dot. And now we have to take another derivative because we have found dx prime over dt prime, but we need to find the derivative of this in order to find the acceleration along x. So let's do it. We have d over dt prime of dx prime over dt prime. This is equal to d over dt prime of x dot minus v over 1 minus v over c squared x dot, like this. And this is equal to d of x dot minus v over 1 minus v over c squared x dot slash dt, because we can take the derivative with respect to time, and then we have dt prime slash dt here. So I'm taking the ratio between these two derivatives using the chain rule as we did earlier. So this is equal to, let's do it, we have 1 over gamma 1 over 1 minus v over c squared x dot, and then here we have x double dot over 1 minus v over c squared times x dot, like this, minus x dot minus v times minus v over c squared x double dot, and then divided by 1 minus v over c squared x dot squared. So if you take this derivative and divide by this derivative, you can rewrite the expression in this form. It's a simple exercise, and we can rewrite this like this. We have 1 over gamma 1 over 1 minus v over c squared x dot cubed times x double dot times 1 minus v over c squared x dot plus x dot minus v times v over c squared x double dot. And now, noting that x dot is equal to v, we can simplify this expression. So we know that x dot is equal to the velocity, after all, of the electron. So if we replace that, we get that this is equal to 1 over gamma 1 over 1 minus v squared over c squared to the third power x double dot times 1 minus v squared over c squared, because this term here will be 0, and therefore this is simply equal to, what is that? It's simply gamma cubed times x double dot. Simple as that. So if we substitute into the x component of Newton's second law for the new frame, the K frame, we have m gamma cubed d squared x dt squared equal to qex, because we know that e prime is equal to ex. Now, working with the y component of Newton's second law, we have something similar. So the procedure is the same. We have to follow the same steps. The calculation will be slightly different because we have a different component. So we have d squared y prime divided by dt prime squared equal to d over dt prime dy prime dt prime equal to, well, first let's write dy prime over dt prime. So let me do it here. Dy prime over dt prime is equal to dy prime over dt over dt prime. So we can use the same steps as before. We have d of y over dt, because y prime is equal to y, and below we have dt prime over dt, so it's d of gamma t minus v over c squared x over dt, and this is equal to y dot divided by gamma 1 minus v over c squared x dot, and therefore we can calculate d squared y prime dt prime squared, which is equal to derivative with respect to t prime of what we just found, y dot over gamma 1 minus v over c squared x dot, which is equal to derivative of y dot over gamma 1 minus v over c squared x dot with respect to dt, and then divide by dt prime over dt. This is equal to 1 over gamma 1 over 1 minus v over c squared x dot, like this. Then we have y double dot over gamma 1 minus v over c squared x dot minus y dot times minus v over c squared x double dot over gamma 1 minus v over c squared x dot squared. And now we know that x double dot is equal to 0 because x dot is equal to v and v is constant, this equation will become d squared y prime with respect to dt prime squared equal to 1 over gamma squared 1 over 1 minus v squared over c squared squared y double dot, and this is equal to gamma squared y double dot due to the definition of gamma. Now if we substitute back into the y component of Newton's second law, we know that we have m d squared y prime dt prime squared equal to q e prime y, and this becomes m gamma squared d squared y dt squared equal to q gamma ey minus v over c dz. So we have found how it changes, how this y coordinate changes. In particular, we can also cancel gamma on both sides, and this is what we get for the y component. Similarly for the z component, so in a very similar manner. So for the z component, you find this. You have m d squared z prime over dt prime squared equal to q e prime z. This becomes m gamma d squared z dt squared equal to q e z plus v over c by. Let me write down also what we found for the x component. We have m dx d squared x prime dt prime squared equal to q e prime x. This becomes m gamma cubed d squared x dt squared equal to q ex, like this. So we have these three equations, and you can see from here that it's as if in this frame K, with respect to which the electron is moving, so the electron is moving with respect to K, but it is stationary with respect to K prime, as you can see, and the mass of the object is different according to these three equations. Actually, we could define, in principle, just like Einstein did in his 1905 paper, two different masses, because you can see that one mass is m gamma cubed in one equation, and in the other equation we have m gamma also here. So one is the so-called transverse mass, this one, and then we also have the longitudinal mass, which is something that physicists abandoned quite fast because it's not really something useful to use the concept of relativistic mass in this manner. But these equations are quite interesting because they show you that a charged body, something charged with a charge, so an electron, is harder to set in motion with respect to an uncharged body because gamma is greater than 1. So we see in particular that the longitudinal mass is the greatest among these two masses, the longitudinal and the transverse. We have two concepts of masses. The longitudinal mass is the greatest, is the largest, because gamma cubed is greater than gamma, since gamma is greater than 1. But even the transverse mass is greater with respect to just m, the mass of the electron at rest. So that's an important concept.